Okay, so we're going to talk about alpha bromination. And we're going to be putting bromine on oxygen, on nitrogen, and on carbon adjacent to a carbonyl group. Before we get started on that, I want to talk briefly about the exam. There's a bishop break day Thursday, so I'll have normal office hours from 7 to 9 if there's no class. We will have our review session starting at 1:30 on Sunday. That seemed to be an okay time for most people. So 1:30 on Sunday, I'll do it here. I will stream it, but you can also come live. So we'll do that. There's a practice exam up. And then I've discovered that there's no class that comes into this classroom after us. So if you don't have a class after us, then you don't have to get up early to start the exam early. You'd actually just be able to go late into the next class hour. So what I plan to do is I'll get here at 7:30, so you can start the exam anytime after 7:30, and the exam will be due, absolute final deadline to submit it at 11:30. So you can pick whatever block of 2.5 to 3 hours you want in that. You can start the exam anytime between 7:30 and 8:30, and you can finish it anytime before 11:30. That'll give maximum flexibility, since I think a lot of people don't have a class immediately following. If you do have a class immediately following and you want extra time, you'll have to start early. But since there's no other class coming in here after us, we can go late if we need to. So hopefully that'll work. That'll give you plenty of time to do the exam. You can look at the practice exam to see about how long it will be. Something you'll probably notice on the practice exam is that there are a fair number of problems taken from the suggested problems. That will probably happen again. So if you don't do the suggested problems, that will be an unwise decision leading into the exam. Since some of those problems are very hard the first time you see them, and you want it to be the second time you see them when you're taking the exam. So let's talk about 3 named reactions that share in common that they are named for someone whose name begins with H, and that they involve bromination adjacent to a carbonyl. And you can actually brominate next to carbonyl groups in aldehydes and ketones, as well as carbonyl groups in some of the carboxylic acid derivatives. So I'm going to do these in kind of the reverse order that I did them on the videos, on the pre-recorded videos. So I'll talk about the Hunsdiecker reaction first. And that is bromination on oxygen. Carboxylic acid. So the net reaction for the Hunsdiecker reaction is to take a carboxylic acid and convert it to an alkyl bromide that has 1 fewer carbon. And CO2 is another product. The reagents for this reaction are base, silver nitrate, and bromine, and this is a free radical chain mechanism. And it is also a reaction that is not in the current edition, the 5th edition of the text. After the 2nd edition, for some reason, they took out the Hunsdiecker reaction. You'll notice that it's basically the opposite of the carbonation. When we do the carbonation to make carboxylic acids, we take the acid bromide, or the alkyl bromide, and we would take that and treat it with magnesium ether to make the magnesium bromide or the gradient reagent, and then we treat that with CO2 solid. And then we do an acid workup. So we know how to go that direction. Now we need to figure out how to go this direction, where we're starting with the carboxylic acid, and we're going to liberate CO2 and end up with the bromide. So that's the Hunsdiecker reaction. And we'll do the Hoffman rearrangement. create rearrangement, RAR. So the Hoffman rearrangement takes amines, primary amines, and makes from it amines with one less carbon, which is again liberated as CO2 gas. Pentaminate would make butylamine or aminobutane. Its base, again, and bromine. And it goes through a bromination on the nitrogen atom. This one involves, obviously, because it's called a rearrangement, there's an alkyl shift. Yeah.
On the line, isn't there 6 carbons?
What's that?
I have 6 carbons in that one.
Chris? Yeah, I can't count today. The amine has 1 less carbon, so the amine has 5. That's twice I counted to 6 incorrectly.
6 must not be your number.
It's a good day. 6 is not my number. Unless it comes in 3, 666, that's my number, right? And the third reaction that starts with H is the Hell-Vollhard. Different spelling, it's not the same Vollhard from our text. Zelinsky reaction, or HBZ. And this reaction converts carboxylic acids to alpha bromocarboxylic acids. And the reagents for this are PDR3, catalytic, and bromine. And it actually goes through the acid bromide as an intermediate. And there's a lot of steps on the Hell-Vollhard-Zelinsky reaction. I didn't cover this at the time when we were talking about alkylation next to a ketone or an aldehyde. I covered it in pre-recorded videos, but I didn't cover it in the actual lecture. That it is possible to convert a ketone, acetone for example, to a bromoketone. And you can do that under either acidic or basic conditions. And if you do it under acidic conditions, it's possible to stop at monobromination, whereas if you do it under basic conditions, it usually doesn't stop, and you get multiple bromination. So you'll end up with lots of bromines, and then it can actually brominate on the other side as well. So it doesn't stop. So these are all the new reactions that we're going to talk about today. The Hunsdiecker reaction, which is bromination on oxygen, followed by a free radical chain mechanism to decompose that. The Hoffman rearrangement, which is bromination on nitrogen, followed by an alkyl shift and a rearrangement. And then the Hell-Vollhard-Zelinsky reaction, which ends up being bromination on carbon adjacent to the carboxylic acid. So I want to go through them one at a time. I want to do the Hunsdiecker reaction first, and then we'll do the Hoffman rearrangement, and then we'll do the Hell-Vollhard-Zelinsky reaction last. And in the process of doing the Hell-Vollhard-Zelinsky reaction, I want to also show you these mechanisms, which we didn't see. They're in pre-recorded videos, but I didn't do them at the time. It's useful to put a bromine adjacent to a carboxylic acid because amino acids are important. And once you have this bromine here, you can displace that with a nitrogen nucleophile and end up with an alpha amino acid. So the Hell-Vollhard-Zelinsky reaction followed by reaction with ammonia is a way to synthetically prepare amino acids. Very useful if what you want is one of the non-common. Like there's 20 common amino acids, and the best way to get those is to digest protein and isolate the amino acid. But if you're trying to synthesize an odd amino acid, if you want to use that in a protein or in a peptide, like a marker or something, alpha amino acids can be synthesized for the Hell-Vollhard-Zelinsky. If I organize this correctly, I can leave the Hunsdiecker reaction up there and get the mechanism on board next minute. So the question I have for you is, if you didn't know the mechanism for the Hunsdiecker reaction, which I'm actually assuming you don't currently, and you were confronted with this reaction, what might you think about doing first when you put these things together? The sodium is going to be a spectator ion, so we'll take that away. And the nitrate is going to be a spectator ion, so we'll take that away. Silver nitrate is the usual source of silver because most silver salts are insoluble, with the exception of acetate and nitrate. So we can't get silver hydroxide as a soluble solid. But basically, by mixing silver nitrate with a basic solution, we're getting silver hydroxide.
Would you detect carbon?
I wouldn't detect carbonyl now.
The carbon oxygen?
Hydroxide probably wouldn't detect the carbonyl either,
Oh, so then I'll take the hydrogen.
because we have an acidic proton. So hydroxide is a pretty hard base. The logical thing for it to do is to deprotonate the carboxylic acid. And that equilibrium constant is going to lie heavily towards the product. And it's basically going to make a silver salt of the carboxylic acid. And was, right? And the equilibrium constant for this reaction is pK of 15, pK of 5,
10 to the minus
about 10 to the 10. So it's not really an equilibrium, right? It's just deprotonation to generate the silver salt. Once you have the silver salt, what might be the next thing you would think of doing?
The one thing that comes to mind is like where we had like, even you could do H2 or like HBr where it attacks the double bond, but that doesn't seem right. So,
I mean,
well, you said it's free radical chain mechanism, so.
yeah, but not yet.
Okay,
That's
never
fine.
mind.
This step isn't free radical.
Okay.
But you've got a nucleophile, and you've got something that can be attacked by nucleophiles, right? You're used to bromine acting as an electrophile, being attacked by double bonds. You could, if you wanted to, use the pi bond to attack the bromine, but you could also just use the negative charge to attack the bromine. So what we're going to do is we're going to form a hypobromite, an acyl hypobromite. That's not a particularly favorable reaction because that OBR bond is really weak. So it could be reversed, and that's why we're using silver. We're using silver in here because silver bromide is an insoluble solid. So we can drive that equilibrium forward by removing the silver and the other bromine through the formation of insoluble silver bromide. Very similar to what we did in the Finkelstein reaction, where we converted an alkyl bromide or an alkyl chloride to an alkyl iodide, and we used the insolubility of the potassium bromide versus potassium iodide to drive that reaction forward. There's another reaction we'll cover later in the amines chapter, which is called the Hofmann Elimination, which is also driven forward by the formation of insoluble silver salts. So the acyl hypobromite is actually the beginning of the free radical change mechanism. And you'll notice I said that it involved bromination on the oxygen of the carboxylic acid. We just accomplished that bromination on the oxygen. These are unstable. So those will spontaneously break that OBR bond, which is very weak, to form a carboxy radical and bromine radical. Anytime you have a really weak bond like that, you can heat it up and you can spontaneously break the bond. So that's one propagation step. You'll notice that the initiation pathway here doesn't involve radicals, right? We're doing an acid-base reaction, and we're doing nucleophilic substitution. There's an acid-base reaction to make the carboxylate salt, and there's a nucleophilic substitution to make the acyl hypobromite. And now we get into the free radical chain. We're breaking that spontaneously, which kind of initiates the reaction. And once you have that, it will start thinking about becoming CO2. So what we'll then do is break this carbon-carbon bond, or the CO2 gas, and an alkyl radical. And the alkyl radical will now react with bromine. And you're used to that reaction. And that's the same reaction that we do when we do free radical bromination under ordinary conditions. Form the alkyl bromide. Generate another bromine. Or alternatively, that alkyl radical can react with another molecule of acyl hypobromite. Form the alkyl bromide and regenerate the carboxy radical. And I guess I shouldn't actually put that on there because now I have to ask you kind of which of these steps are in fact the propagation steps. So these are possible reactions that could occur, right? Spontaneous cleavage of the weak OBR bond, decomposition of that carboxy radical or CO2 in the alkyl radical, and then that alkyl radical can react with any bromine source that happens to be present. So how do we decide which are the propagation steps of the free radical chain mechanism. The propagation steps have to add up to give the overall reaction. And the overall reaction is the acyl hypobromide generating the alkyl bromide and CO2 gas. Right, this is the overall reaction.
It'll take the bottom one.
So the propagation steps should be reactions that add up to that. So we need the alkyl radical to appear as a product in one and reactant to the other, and we need the carboxy radical to be reactant in one and product in the other. So your first propagation step is the decomposition of the carboxy radical to form CO2 and the alkyl radical, and your second propagation step is the reaction of the alkyl radical with the acyl hypobromide for the carboxy radicals. So you'll notice now that we have the carboxy radical, which will cancel out, and we have the alkyl radical, which will cancel out, and our net reaction is the acyl hypobromide forming CO2 plus the
Wait,
alkyl
so the
bromide.
last arrow is not a propagation step?
So this is the initiation, right? The
Oh.
breaking of the bond to form the actual carboxy radical, and then that carboxy radical initiates the chain by spontaneously blowing out the CO2. This reaction probably doesn't occur very often because most of the bromine will have been consumed in making the acyl hypobromide in the first place and the silver bromide. But if there's any excess bromine left around, it will do this as well. So it's a fairly straightforward mechanism. Right? It's a acid-base reaction followed by a nucleophilic substitution to make this acyl bromide, acyl hypobromide. That spontaneously cleaves to initiate the free radical chain, and then you have your two propagation steps where that blows out CO2 and then forms the alkyl bromide. So not too difficult. Right? It's only a two-step propagation, similar to other propagation steps that we've worked with. I'm going to save that. Are there questions on the Hunsdiecker reaction?